Okay, so this is another exercise in the related rates problems, and it has a little bit of a wrinkle. Let's see what this one's all about. So we have a rocket that's shot vertically upward, and its height after t seconds is given by s of t equals 400t minus 16t squared. An observer is standing 1800 feet from the rocket at launch. How fast is the distance from the observer to the rocket changing when the rocket is still rising and is 2400 feet above the ground? Do you have a picture of it in your mind? See if you can draw a sketch of what's happening, and pause the video, and we'll be back to discuss our pictures. Okay, are you back? Let's give us a little bit more room here. So let's say this is the position of the rocket at launch, and so the person that's standing here is going to be 1800 feet away, right? And so then the rocket is up here somewhere. It's going vertical, and so then this would be the distance, the length of this hypotenuse here. Probably giving it away there. Length of the hypotenuse will be the what we're looking for. How fast is the distance changing? So the length of the hypotenuse is the distance, so we're actually looking for the rate of change of that distance. And so I need to label. So can I label anything? Let's see. This is going to be this is changing. I guess you can't see what I'm pointing at. This is changing, the red line here. And how big is that? That's going to be s of t, right? And then, so let's go ahead and call our distance, shall we call it x of t, I guess? Okay, and now you see that we have a right triangle. And do we have all the information we need? Maybe. So we want to find dx over dt when s of t equals 2400, right? Oh, that seems reasonable. Okay, I'm going to pause here, or you should pause here, and pause and see if you can come up with a formula that relates the variables. Okay, that probably didn't take too much time. You're using the Pythagorean theorem, so therefore x squared is equal to 1800. Well, let me be explicit here, because x and s depend on t, so that's x of t squared equals s of t squared plus 1800 squared. Okay, now I could have taken the square root of both sides, but it's kind of a pain to have to differentiate the square root, so I don't usually do that. Let's see if we can get away with that though, because now when I differentiate, right, I'm going to have 2x times dx over dt, right? So I'm having to use the chain rule on this side. And actually it's going to be the same thing on the for the s of t, right? So 2 times s times ds over dt. And then the 1800 is going to be 0. Alright, so now when I'm solving this, I can get rid of the 2's, I can get rid of the 0. And so what I'm trying to find then is find dx over dt, so find this quantity when s is equal to 2400. So I know that's 2400, but I still need to find ds over dt, and then I'll also need the x, right? So how am I going to find x? I know that x squared is equal to x squared is here, let me say, make a note here. Find x when s equals 2400. Okay, so that means x squared is equal to 2400 squared plus 1800 squared from the Pythagorean theorem. Good. And so if I look that up on my calculator, what do I get? Ooh, it's an actual perfect square. X is equal to 3000. Good. All right. So I've got 3000 here for this one. And I've got 2400 there. I just need ds over dt now. So that's easy to compute. I know what S of t is, right? Up there. So therefore, maybe I should write it down here. S of t is 400t minus 16t squared. So we'll just say recall S of t is equal to 400t minus 16t squared. Good. So ds over dt is equal to 400 minus 32t. Now I'm in a quandary, right? Because I need a constant here for my ds over dt. It should not be a function of t when I solve up here for my equation. So what am I going to do? Well, we need t, right? Which t do I need? I need the time at which something is known here, 2400. Need t for which, need t for which s equals 2400. Good. Okay. So let's see. How am I going to do that? Well, I know that S of t is the original equation. I know the original equation here. So I'm just going to substitute 2400 in for s and see what I get. So I'll have 2400 equals 400t minus 16t squared. And so if I bring things over so it looks like a regular quadratic. Good. I've got that quadratic equation. And in fact, that actually factors nicely. Let's go ahead and see if we can simplify that a little bit. 25t, 150 equals 0. And it just turns out that this simplifies to t minus 10 times t minus 15 equals 0. So now I have to choose. Do I use t equals 10 or t equals 15? Well, why would there be two times for which s is equal to 2400? Well, remember, this is a rocket going up. So the rocket's going to pass 2400 on its way up, and then it's going to be passing 2400 on the way down. So we see here that this is going to be time 10 on the way up and time 15 on the way down, right? And so we'll use t equals 10 there. Good. And so if we plug in t equals 10 to ds over dt, so we look at ds over dt when t equals 10, then we have 400 minus 32 times 10. And so ds over dt is equal to 80, it looks like, huh? Good. Now, we have our last number that went in here. That's an 80. Good. So let's summarize here. I'm running out of space, so let me transfer all of this information down below here. I'll pause while I do that. Alright, so I just put our equation down here, and so we see that I think we found all the variables that we need. So therefore, we see that dx over dt must be 2400 times 80 divided by 3000. Right, and so using our calculator, what do we get? 64. Good. All right. So, what does that mean? Does that sound reasonable, by the way? If you look up here at what we were doing, this 1800 here is fixed. This is going up, and we saw that the rate of change was like an 80, right? And so the question is, how fast is this changing? And we said that's changing at a rate of 64 feet per second when S of t is right at 2400. Good. And so that does seem reasonable, just looking it over. Good. And so this was a little bit more complicated kind of a problem, and it was complicated by the fact that S of t was actually some known function that we had to use in order to get some of the other values. Very good. So I think this is probably the last example I'll do. I may do some more if people ask. Otherwise, I will see you later.